When you ask a large language model to evaluate a crop yield based on physical coordinates, you often get a response that looks like this. The system attempts the calculation, races through the prompt, and aborts into a hard failure, or worse, invents the data entirely. Modern foundation models possess immense reasoning capacity. They write complex code, summarize legal documents, and synthesize logic. But they have zero deterministic knowledge of the physical world. Without an external grounding layer, they cannot independently verify if a specific latitude and longitude in Iowa is prime loam or solid rock. You might think the solution is pointing the AI directly at government databases like the USDA. But those repositories were built decades ago for human researchers. They rely on fragmented, non-standardized architectures with complex taxonomies. An autonomous AI agent cannot reliably parse a multi-layered PDF table or a localized soil nomenclature system on the fly. Standard map services and generalized geospatial APIs fail here as well. They accurately resolve coordinates and confirm a field's location, but they lack the agronomic and chemical depth required to explain the actual soil composition or local water contamination risk. This creates a strict requirement for what we call machine legibility. For autonomous AI consumption, physical data must be mathematically structured and deterministically formatted. The AI agent needs a direct, unambiguous JSON payload that dictates exact soil composition, drainage classification, and organic matter percentage. If you run autonomous workflows in agriculture, crop insurance underwriting, or environmental compliance without that deterministic data structure, the agent will inevitably fill the gaps with statistical probabilities. It will hallucinate the physical reality. Preventing these real-world execution failures requires abandoning traditional API design. Autonomous systems require a dedicated, machine-legible environmental intelligence layer. Sourcing this intelligence becomes exponentially more complex when you expand beyond a single region. The physical world is measured by different institutions, creating massive, siloed datasets that resist easy integration. In the United States, environmental taxonomy is dictated primarily by the USDA's SSRGO database, a massive repository of hyperlocal soil and landform characteristics. Cross the Atlantic, and that standard disappears. Ireland maps its land through the TGASC database, while the United Kingdom relies on the UK Soil Observatory, using completely different classification schemas. 3 distinct, unconnected data columns rise from the US, Ireland, and the UK. Their structurally incompatible data blocks cause immediate processing gridlock when an autonomous agent attempts direct ingestion. For human developers, fixing this requires building and maintaining custom translation pipelines for 6 different international agencies, mapping specialized data points into a unified logic model. This fragmentation prevents developers from taking a regional agtech tool and deploying it globally. The application logic works, but the underlying data layer breaks. Deploying reliable agentic workflows on an international scale requires unifying these disparate datasets at the foundational infrastructure level, well before the LLM receives the prompt. LeafEngines SDK version 3.0 was engineered specifically to solve this geographic fragmentation problem. A bounding box-aware routing engine instantly maps a downward pathway to the correct regional database adapter. It handles geographic selection automatically, eliminating the need for the agent to know the correct country. Raw intelligence from the regional adapter passes through a universal harmonization funnel, the standardized soil data schema. Mismatched data blocks emerge as identical structured JSON packets, including explicit confidence scores. The schema also strictly enforces a data freshness timestamp. An agent assessing crop viability requires mathematical proof that the environmental model reflects current conditions, rather than a decade-old survey. Crucially, the system performs algorithmic translation on the terminology itself, mapping a hyper-specific local soil type into a globally recognized harmonized soil type. This translation process operates entirely beneath the API surface. The large language model never sees the routing logic, the source mismatches, or the terminology mapping. By enforcing a strict deterministic schema, LeafEngines abstracts the complexity of geography away. It turns the physical characteristics of global soil into mathematically actionable intelligence. Even with perfect data harmonization, traditional REST APIs create friction.
they inherently assume a human developer is reading the documentation, configuring endpoints, and handling pagination manually. Integrating an autonomous agent requires a shift from passive endpoints to the Model Context Protocol, an interface built specifically for agent discovery and tool execution. Looking at this code, an AI plugin manifest file allows an agent to dynamically read capabilities and map required parameters. This configures its own connection to the LeafEngines server on the right. Through this connection, the server natively exposes 9 specific tools. An LLM instantly recognizes and triggers functions like a soil profile analysis or a risk indicator generator, exactly when its reasoning loop requires that data. Establishing the connection solves the integration problem, but managing the traffic requires specific infrastructure. Autonomous agents do not consume data in predictable, linear human patterns. Unlike the gentle curve of human UI traffic, an autonomous agent generates vertical spikes of up to 600 requests per minute. An agent-tier architecture must absorb these high-capacity bursts without blocking them. This requires per-completion metered billing, ensuring developers pay strictly for actionable intelligence delivered, rather than raw server requests or rate-limited retries. True machine legibility relies on a 2-part architecture. It requires deep, standardized data schemas to prevent hallucinations, backed by server infrastructure built exclusively for autonomous execution patterns. With the routing and infrastructure layers established, we can see exactly how this executes in the field. What you are watching is a high-contrast digital map of an agricultural field, autonomously generating color-coded variable rate fertilizer zones. Using the complete LeafEngines stack, an AI agent analyzes hyperlocal soil profiles, processes topographical constraints, and writes a complete ISO-bus-compatible equipment prescription autonomously with mathematical certainty. In the enterprise sector, compliance agents chain these exact same tools together to instantly verify ESG carbon credits, pulling historical crop rotations and soil composition data to calculate sequestration metrics without human review. This pipeline flows from ingestion to execution. Disparate international data sources feed into the bounding box router, unify through the standardized schema, and serve through the MCP server directly into the agent application. Notice the unbroken flow of data passing cleanly through every layer. This architecture ensures that physical world parameters are no longer locked inside human-centric dashboards. By converting fragmented government data into deterministic tools, developers can build agents that operate with the same precision as traditional software. The growth of the agentic economy depends on this transition from human-readable documentation to machine-legible context. When data is structured for autonomous execution, the primary technical bottleneck shifts from complex data integration to high-level reasoning.